And a big thanks to Justin for being okay with moving his lecture so that you guys get fun. So now let's have a bit more fun with Justin's lecture. So lecture 2, please go ahead.
Okay, well, thanks a lot. Can you hear me okay?
Yeah.
Okay,
Yeah.
Good. Yeah, so let me start out by saying that yesterday somebody asked about the extent to which ordinary CDM can reproduce this mass discrepancy acceleration relation or this MON relation. So I wanted to at least give you a nice reference for this. So there is a nice paper by Harry Desmond. And I'll give you the archive number. And this is sort of a nice semi-analytical derivation of how the extent to which CDM can do this MON relation. And actually, remarkably, he did this as a PhD student. Really a nice paper. Actually, I think that this guy was really, it was his destiny to write this paper because his name is Desmond. Okay. Anyways, I recommend having a look, and it makes the point that I mentioned yesterday. Okay, so yesterday we left off by discussing, mentioning that superfluidity, if you want a working definition of superfluidity, is that it's the spontaneous breaking of a global U1, which enforces conservation of particle number. There's a small wrinkle here, as we'll discuss, which is that this spontaneous breaking is not a vacuum spontaneous breaking, but rather it has to do with finite charge density of the state of interest. We'll make that precise in a moment. So this is a finite charge density, which captures the physical fact that the condensate has a finite number density, obviously. So as we said, we will describe this in a field theory context, which it's simplest for a pedagogical reason to start from a relativistic field theory and then later on take the non-relativistic limit. So our working example, as a simplest example, is simply a massive complex scalar field. So here's the Lagrangian. We have kinetic term. We have a mass term for this guy. And of course, we need interactions to produce superfluidity. So the simplest form of interactions would be quartic minus g/2 psi to the fourth. And for stability, as we will see, this quartic coupling constant has to be positive. This can be seen here, obviously, to have a bounded potential. And we will see this later in the effective theory of phonons, that it is also a requirement. Now, obviously, this theory enjoys a U1 invariance, which act as multiplication by a overall phase of this field. So I can clearly rescale psi by an arbitrary phase, which is a global U1 symmetry. And associated with this symmetry is a conserved current by Noether's theorem. So the conserved Noether current associated with this symmetry is simply given by J mu is I psi star E mu psi minus psi D mu psi star, like so. And of course, we will be interested in the corresponding charge density, which is the 0th component of this 4-vector current. Charge density associated with this is nothing but the number density of particles. So this is the 0th component of J, and it can be written therefore as minus I psi star dt psi minus psi dt psi star. The minus sign is because I've lowered the time derivative index. I'm working in the minus plus 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 signature. And so there we have it. So let's start out by describing the condensate properties of this superfluid. So for the condensate, so here for the condensate, we will make an approximation. We're going to approximate it in the mean field, or equivalently semi-classical approximation. So in this approximation, in other words, we are ignoring the back reaction of quantum fluctuations onto this condensate. And as a result, this condensate profile simply satisfies the classical equation of motion. So the classical equation of motion for this condensate satisfies plus.
I have a quick question.
Yes.
Could you say a little bit more about what this mean field approximation is? I didn't quite get that.
Yeah, so of course, the equation of motion that I'm writing down would hold in the Heisenberg picture as an operator statement. Here, the approximation amounts to treating this operator psi for the condensate as an ordinary function, as a wave function. Okay, so that's the mean field. And essentially underlying this assumption is that quantum fluctuations, are not back reacting. We're ignoring the back reaction of those fluctuations onto the condensate. So it simply satisfies the classical equation of motion.
Okay, thank you. And I think there's more.
I'm sorry, I don't understand what you mean by this back reacting.
Yeah, so in general, this is an interacting theory, right? So if one of the standard approaches is the Bogolyubov approximation, right? And what you do there is you expand the field. So the alternative would be to express the field as this condensate psi naught rather, plus quantum fluctuation delta psi, right? There's a very simple way to think about this really, which is familiar from our ordinary field theory treatment, which is, as you know, that in the saddle point approximation, right? You would write the wave functional, the partition function, as e to the I s. Is S classical, right? So around the saddle point, but then as you know, there's a fluctuation determinant, and that's precisely what we're ignoring in this description. Does that make sense?
Yes, thank you.
Yeah. Yeah, I mean, another way to say this is in the Bogolyubov treatment, what you would do is you would write down the corresponding Hamiltonian associated with this Lagrangian, and when you expand, you see that you will pick up term which will involve a quadratic order. In this guy, you will pick up terms that are quadratic in the fluctuations, thereby averaging over them, which corrects the equation of motion for the condensate. So for simplicity, we ignore those effects. Yeah, thanks for doing that, those nice questions. Okay, so this is the equation of motion that our condensate satisfies. And to solve it, we will make the following ansatz. The ansatz of interest, I claim, is that psi naught. We are interested, of course, for the purpose of this discussion, in a homogeneous, spatially homogeneous condensate. So it can only depend on time, and so we will write it as an overall amplitude times e to the I mu sub r t. So this is our ansatz, where this phase mu sub r is identified as the relativistic. That's why I put the little subscript r, the relativistic chemical potential. And we will come back later on to motivate or justify why this ought to be identified with the chemical potential. For the moment, let's just take it as a definition of mu sub r, okay? Sorry, I'm sitting outside actually because it's so nice here that but that also causes a bit of background noise. So I apologize for that. Okay, so very nice. You plug this into the above equation of motion. So you substitute and you find the following relationship among these parameters, you find that the relativistic chemical potential squared is equal to m squared plus gv squared. Okay, I hope this is clear from the above relation. And now to relate to the non-relativistic chemical potential, which we discussed yesterday, to relate mu sub r to a non-relativistic chemical potential, denoted by mu, we take the non-relativistic limit of this result, in which the mass is considered large compared to the other scales. So what do we obtain? Well, in this limit, first of all, I write mu sub r as the square root of m squared plus gv squared. And I simply Taylor expand the square root, pull out the m out of the square root, Taylor expand, and you can clearly convince yourself that the result would be m plus gv squared over 2m. Like so. The first term is clearly identified as the rest mass energy of the dark matter particle, while the second term clearly owes to interactions, given that it's proportional to g. So this is an interaction slash potential energy between particles. And it is this term, therefore, that we associate with the non-relativistic chemical potential, okay? Which makes ample sense. The only difference, if you want, between the relativistic chemical potential and the non-relativistic counterpart is simply the rest mass energy. Oh, by the way, somebody yesterday asked about or pointed out that mu could be positive in the presence of interaction. So let me just make a little quick note about this. So you'll recall yesterday that when we discussed the free Bose gas, I just want to make contact with what we said yesterday. So the free Bose gas, you'll remember, has a chemical potential which ranges between minus infinity and 0. That is to say, it's negative. But keep in mind here that we are working at 0 temperature. And in particular, for T going to 0, this free chemical potential also goes to 0, okay? So in other words, now that we're at T equals 0, the free, if you want, the free chemical potential would vanish, but now we're also adding, turning on interactions, and those interactions push the chemical potential slightly to the positive side, as shown here, okay? Hope this makes sense.
I have a quick question.
Yes, please.
Thanks. So it looks like when we do this derivation to get that mu squared, we are assuming that mu is not explicitly time dependent. Is that true? And if so, why is that a good assumption?
If you want, it's an ansatz that, yeah, it's an ansatz for this condensate wave function. We want to assume, I mean, in principle, we're allowed to make any ansatz we want as long as it satisfies the equation, the simplest ansatz possible. If you want, this defines what kind of condensate we want to talk about. So this condensate is spatially homogeneous and has very simple time dependence, which ensures, importantly, that the number density of particles will be constant. Simple as that. Yeah, if you want, it's almost forced upon you, isn't it? Because if what this equation of motion implies is a continuity equation for the condensate, right? The usual continuity equation would be that the time derivative of the number density plus grad J is equal to 0, okay? Where this is the spatial part of the current. And if you assume homogeneity, that is to say your superfluid doesn't have velocity, then it enforces that the number density must be constant. So it's just to say that this is a self-consistent set of assumptions.
So in the case of dark matter, is it a good assumption to say that
great question. Yeah, great question. Oh, that's a fantastic question. So good. So now, very good. So a couple of things to be said. Of course, in the cosmological context, as you correctly point out, what we will want to do, first of all, on the background, will be to couple this to the metric. And there we will see that the correct behavior of the condensate in the presence of an expanding FRW background will be instead that the number density scales as 1 over the volume, as you would expect, okay? Because this is a non-relativistic gas to first approximation and therefore dilutes as CDM. Secondly, as you also are asking, in the presence of, in a galaxy, clearly the assumption that the condensate is homogeneous also will break down, but you'll see how this will come about. This will not come about by mu itself becoming spatially dependent, but rather it will come from including the effect of the gravitational potential inside, as part of the superfluid description. You'll see that a bit later today. Yeah, this is a brilliant question. Yeah, thanks.
Okay, thank you.
Yeah. Any other questions so far?
I think we're good.
We're good? Okay. Yes, very nice. Okay, so in particular, to make explicit the point I just said, if we now substitute this ansatz, so this ansatz for the condensate into the charge density, into N, we discover that N, it's a simple exercise. So here's N, right? It was just some combination of time derivatives of psi, like so. And when you make that substitution, it's a simple exercise that you can check. You obtain that this is twice the relativistic chemical potential times V squared. So V squared, if you want, crucially sets, so this amplitude V sets the number density of the condensate. And in the non-relativistic approximation, we can trade mu sub r simply for the rest mass. So this is twice mv squared approximately in the non-relativistic approximation. Now, as a side result of this, you see here we had one relationship between mu and gv squared and m. And there's a second relationship now between n and mv squared. So if you combine the two, you obtain a relationship between the number density and the chemical potential, which is a useful thing to know. So clearly the result is that n is equal to 4m squared mu divided by g. We will put this result on the back burner, and later on we will verify it by different means. But suffice to say now, this gives us a clear relationship between two thermodynamic variables, the number density and the chemical potential. All right, so this was the story for the condensate. And now we are, of course, interested in excitations and phonons. So we expect from Goldstone's theorem, we are spontaneously broken a symmetry, a U1 symmetry, and as a result, we expect a massless / gapless excitation. And this Goldstone boson will be associated with the phonon excitation of the superfluid. Okay, so that's what we want to show next. So to study excitations, we have to go beyond this simple homogeneous condensate picture and expand the field psi. Now I'm going to expand it as 1 over root 2. I'll write it as V plus. So here I think there's a root 2 difference with my convention above, but it doesn't really matter. 1 over root 2V plus I perturb both the amplitude. So I'm going to call the perturbation of the amplitude as rho. And as well, I perturb the phase. So I had e to the I mu sub RT, and now I perturb it with pi fluctuation, which is also space-time dependent, like so. So we've perturbed both the amplitude and the phase, and we substitute this back into the Lagrangian. And thereby we obtain the following result, that the Lagrangian upon the substitution is minus 1/2 d mu rho squared. So ordinary kinetic term for rho plus 1/2 V plus rho squared, GV squared, plus 2 mu phi dot, this is mu sub r, plus phi dot squared minus grad phi squared. And lastly, from the quartic term, we obtain minus g over 8 v plus rho to the fourth. Okay, so what I've done here is I've used, in particular, when you make the substitution, you use the relationship, the background relationship for mu sub r being m squared plus gv squared. This will cancel the m squared. If you go back to the Lagrangian, when you do that, this will cancel this term, okay? But leaving you with additional terms coming in particular from this kinetic term. And this is the final result shown here. Okay, so you recognize here, this is coming from the quartic. This stuff over here is coming from the kinetic term upon substituting the onsets. Make sense? All righty. So now at this point, let us focus a little bit on the rho dependence of this Lagrangian. Okay, so the rho dependence of this Lagrangian in particular is minus 1/2. There's an ordinary kinetic term for rho. And now you see, if I were to expand quadratic order in rho, okay, so there's some quadratic dependence on rho, which will come from here. There's some quadratic dependence on rho, which will come from there. And when you put it together, you can easily show, and I welcome you to check this, you'll obtain an overall minus 1/4 gv squared rho squared. And of course, plus higher order terms, additional terms here. And so clearly this rho field immediately is recognized as having a mass. Okay, it has a mass for rho given by 1/2 gv squared. It's the massive mode as you'd expect. And so this is like the analog of the Higgs field. This is the massive mode. And so our working assumption is that if you work at sufficiently low energy or sufficiently low momentum, then we can basically integrate out this Higgs mode being massive. And as a result, we can work in a gradient or derivative expansion in this radial mode. Okay, so at low energy, in other words, at low energy / momentum, low relative to this mass scale, we are justified in integrating out this massive mode and integrate out rho. And more precisely, what we do, if you want, is a perturbative expansion in gradients of this rho. Okay, so basically we treat its derivatives perturbatively. Okay, so this is just a fancy way to say that we work order by order. To 0th order, we treat rho as homogeneous. So to 0th order, in this lecture, we'll just work it to 0th order, but I will let you derive as an exercise the first order correction to the dispersion relation, as we'll see. So, but first, let's just work to 0th order, which is to say that I can completely drop all gradients and time derivatives of rho and just integrate it out. It becomes an auxiliary field, which I can easily solve for. So to 0th order, once I vary with respect to rho, so in other words, we ignore to 0th order gradients of rho. And therefore, the equation of motion for rho is that of an auxiliary field, which gives me that V plus rho times this combination of GV squared plus 2 relativistic chemical potential pi dot plus pi dot squared minus gradient pi squared minus G over 2 V plus rho cubed. That whole shebang is equal to 0. Yeah? So very nice. This is trivial to solve. Okay, so the solution as a result I can solve for rho as being, so I obtain G over 2 V plus, V plus rho squared is equal to G V squared plus 2 mu sub r pi dot plus pi dot squared minus grad pi squared. And this combination over here, by the way, I'm a little confused about a factor of 2 here. Maybe you guys can just polish this after the fact. I think when you set pi and rho to 0, you should of course get a trivial equation. So probably there's no 2 here on the left-hand side. I'll let you guys clean this up after the fact, okay? But anyway, you get a relationship of this form, and this guy on the right-hand side, I will define this whole combination, I will define to be x sub r, okay? What I'm gonna call relativistic capital X. When you substitute then this back into the Lagrangian, we've solved for the auxiliary field, we substitute back in. So substituting back into the Lagrangian, we obtain that L, right? So you see, if you go back to the Lagrangian, right? Go back to here, what we found is that this combination, basically V plus rho squared, is what we call X. Technically, it's actually X over G, the coupling constant. It's multiplied by X itself, while this term gives you something of order X squared. So they both of order X squared, they combine together, and the end result is the following. You get that this is 1 over 2G relativistic X all squared. And to be perfectly clear now, you see that we've integrated out rho. So this theory that I'm writing down in terms of this X really is a theory of pi. The only dynamical degree of freedom at this point is pi. So far, so good. Any questions?
Yeah, I have one. Thanks. So just stepping back a little bit, trying to understand what's really going on here. So when we define psi, is the way to think about it that like all of our space and time information is encoded in this row, and otherwise we just have this v with the exponential, which I guess also has the time, but.
Yeah, so to start with, we perturb both the amplitude and the phase, both with space-time dependence. So these are my in principle, two fields. But since we've spontaneously broken the U1, since effectively I'm expanding around the spontaneously broken U1, we expect one of these degrees of freedom to be massive and the other one to be massless. And that's precisely what's going on. So the rho field we immediately notice is a massive field, like the Higgs. So happily we can integrate it out at sufficiently low energy. And as a result, so this is what we've done here, it becomes an auxiliary field once you've ignored its gradients at low energy. And as an auxiliary field, we solve for it, substitute back in, and what is left is an effective Lagrangian that only involves pi itself. Okay, so one way to think about it is that there are here in this Lagrangian, if you go back to this Lagrangian, a physical way to think about it is that you see here that there are some interactions here involving rho. If I were to expand this whole shebang out, there are some interactions, like for example, rho squared times pi dot. There are some rho squared pi dot squared terms. So all that stuff are interactions that involve rho, but once you integrate out rho, it just gives you simply nonlinear interactions among pi itself. And that end result is what's captured over here.
Okay, that clears things up. Thank you.
Thanks. Very nice. So at this point, now it's the right moment to actually take the non-relativistic limit, which is really what we're interested in ultimately. So let us take this non-relativistic limit appropriate for a non-relativistic superfluid. All right, so the non-relativistic limit means what? It means, first of all, as we've said above, that the relativistic chemical potential is approximately given by the rest mass energy, Okay, this makes sense. In the non-relativistic limit, the energy cost of finding one particle is predominantly given by the rest mass energy. So that's very nice. And secondly, time derivatives of this field, as well as its gradients, are small relative to m. So we assume that pi dot, therefore, is much less than m. Okay, so if you look now at this definition of x sub r over here above, you see in particular, so this mu sub r will be approximately m, if you see this. And so this term is m times pi dot, which is clearly dominant relative to pi dot squared. Okay, so we are justified, therefore, in eliminating the pi dot squared term. At this point, you may be tempted. You may get a bit carried away and say, okay, now I'm also going to drop all the gradient terms because they're also quadratic in pi. But you have to be careful because in the non-relativistic limit, what happens is that spatial gradients, as you know from gravity, right? Spatial gradients are far more dominant than time derivative terms. So although the time derivative term comes multiplied by m, it is itself suppressed relative to spatial gradients. So in fact, you'll see that the correct approximation is in fact to keep the grad pi squared. Okay, if you don't believe me, we just carry on and you'll see that it's legitimate to keep it. But we can drop the pi dot squared term so that x sub r in this non-relativistic limit becomes approximately equal to gv squared plus 2m pi dot, one second. Just give me one moment. I want to fix something. GV squared. Where was my new, oh yeah, no, it's okay. All right, sorry about that, I got distracted. Okay, so here we are. I dropped the pi dot squared, so this is twice m pi dot, but I do keep the gradient pi squared term, like so. And at this point, we may as well pull out the factor of 2m for convenience. So I pull out the factor of 2m, leaving me with gv squared over 2m plus pi dot minus grad pi squared over 2m. You see, and immediately here you recognize this combination as the chemical potential, the non-relativistic chemical potential, which if you scroll back up a little bit, you see that this is precisely what we had identified in equation 1. So very nicely, this involves the chemical potential mu. So in other words, this relativistic x is simply twice the mass, mu plus pi dot minus grad pi squared over 2m. And now it's just a matter of definition, but it's convenient to define a non-relativistic x that I'm simply calling x to be this particular combination here. So this I'm going to define to be the non-relativistic x kinetic variable. Okay? So when you plug it in, so you see basically that x sub r is just twice the mass times non-relativistic x. You plug that in the above Lagrangian, trivially, you end up with a non-relativistic Lagrangian for the Goldstone boson, which is given by twice the mass squared divided by the coupling constant times this non-relativistic x variable all squared, where again, x, just for completeness, let me rewrite it. X is defined to be mu plus pi dot minus grad pi squared over 2m, like so. Is this crystal clear? Any questions? Okie dokie. Now, this is a nice non-relativistic story, but we have yet to get back to our task of studying these Goldstone bosons, these phonons. So now let's do it. So we take this Lagrangian and we will expand it to quadratic order in pi. In other words, we are interested now in small fluctuations in this phase. And it's a simple exercise, right? We do it, we expand to quadratic order, and we obtain the following. So L at quadratic order. So first of all, what I'm doing is squaring X, no? So I get a term proportional to mu squared. This gives me twice M squared mu squared over G. Okay, that's the leading term. Then from the cross term between mu and pi, I obtain a term which is plus 4m squared mu over G times pi dot. And then I get terms that are quadratic in pi, and those are in two flavors. First of all, when I square X, I'm gonna get a pi dot squared term. So this will be plus 2m squared over G times pi dot squared. And now there is a term coming from the gradient pi squared term. Notice that it's already quadratic. So the only contribution from this guy is coming from the cross term with mu. Okay, and when you work it out, this will give you minus mu over m times grad pi squared. And that's it at quadratic order. Whoops, what happened? One moment. Okay, sorry about this. Very nice. Okay, now let's examine these different terms. So first of all, the first term is clearly just a constant. It's an irrelevant constant. We ignore it. The second term is a total derivative. That's clear. But it's not devoid of physical meaning. That total derivative term, its coefficient, we immediately recognize as it should be. So this guy over here, we recognize it as the conserved charge density, which makes perfect sense. The term proportional to pi dot has to be n, the number density, and indeed it is. That's a very nice check. But it's a total derivative, so it doesn't affect the dynamics of pi. The relative term, of course, for pi is the next terms, which are the quadratic terms. And from this, you immediately notice that this pi behaves as wave excitations, and we're propagating with a sound speed given by mu over m. So in other words, the dispersion relation for pi that we immediately read off is a linear dispersion relation, omega being proportional to k, where the sound speed, where cs squared is equal to mu divided by m. And if you substitute for mu in terms of n, this is equivalently gn over 4m cubed. And that's an important result. It tells us that the excitations of our condensate are waves, they're sound waves, and these are the excitations that we identify as phonons. So these are precisely phonons. Now, this dispersion relation mentioned above was obtained by working to zeroth order in derivatives of rho. You can systematically correct it by keeping perturbatively gradients of rho. Okay, so you would take the equation of motion we wrote down over here for rho and include a gradient term from the kinetic term for rho and keep its effect perturbatively, thereby correcting your solution for rho, plug it back in, etc. And what you'll find ultimately, and I'm going to leave it to you as an exercise. It's a nice exercise that you can do in the privacy of your room. That ultimately, if you work to subleading order in the gradients of rho, you'll find a modified dispersion relation, which takes the form omega k squared is equal to cs squared k squared plus k to the fourth divided by 4m squared. And if you've encountered the Bogolyubov approach to the description of weakly coupled Bose gases, as we're treating them now, you will recognize this, this dispersion relation from Bogolyubov treatment, okay? And in particular, it has two familiar contributions. The first one is the phonon wave term. And the second term, you recognize as precisely the dispersion relation you would obtain for a non-relativistic particle. In other words, if you take the limit that the gas is non-interacting, the limit G goes to 0, in this limit, clearly from over here, the sound speed also goes to 0. By the way, this tells us that in order to have propagating sound waves, this Bose gas has to be interacting. Okay, so that's an important lesson. But in this limit, therefore, since the sound speed goes to 0, the phonons are absent, and you have, therefore, no superfluidity. And correspondingly, the dispersion relation in this limit approaches k squared over 2m. Okay, that's what the above tells us, which is precisely the standard dispersion relation of non-relativistic physics, of non-relativistic particles. That's comment number one. Comment number two is another important lesson, right? You see from the form of the sound speed over here that for the sound speed squared to be positive, that is to say, for waves not to propagate with imaginary sound speed, which would imply a gradient instability, you need G to be positive. So stability, that is to say positive sound speed squared, okay, requires that the coupling constant G be positive, which describes therefore repulsive interactions between particles. So I think somebody made the comment yesterday, indeed relating stability and the sign of the interactions. And this confirms that point that you need repulsive interactions between particles in order to have stable propagation of waves. We also saw this from the get-go, that our theory in terms of the complex scalar fields, in order to have a potential that was bounded from below, there we have it, required also G positive. So everything at the end of the day is sort of self-consistent. Let me make one more remark about this particular working example, which is to say that we can now go back and derive some thermodynamic property of this condensate, in particular its equation of state. So we go back to the condensate now, and if I set the fluctuations, the phonons to 0, set pi equal to 0, then in this limit, if I set pi equal to 0, this variable x introduced above here will simply be equal to the chemical potential in this limit. So when I set pi equal to 0, x is equal to mu. And therefore, the Lagrangian, in this particular case, simply reduces to twice m squared over g times mu squared. And the Lagrangian, you'll recall from quantum field theory, describes the pressure of the system. And since we're expressing here the pressure in terms of the chemical potential, this is P as a function of mu. It is therefore the grand canonical equation of state for the system. So this is the pressure. Okay, in general, of course, it would also depend on temperature, but we've set the temperature to 0, hence it's only a function of mu. And from standard thermodynamic relation, we know that the number density is obtained as the derivative of the pressure with respect to mu at constant temperature. Of course, temperature is 0, so it doesn't concern us. There's a question, I think.
Yeah, thank you. Maybe I'm just misremembering, but I don't think I remember ever hearing that or seeing this Lagrangian equals pressure thing. Is that just because the Lagrangian is describing the interactions and the pressure is coming from those interactions? Or is there something before there?
Yeah, pretty much. I mean, that's a nice intuitive way to say it. Absolutely. Another way to think about it is just to work it out. If you take a quantum field theory and you vary with respect to the metric to obtain the components of the stress energy tensor, you'll find that indeed the Lagrangian is equals the pressure. Yeah, I mean, one way, I mean, a simple way to see it, for instance, is in the case of take a homogeneous scalar field, okay, like in inflation, right? You know, so the Lagrangian is minus a half d phi squared minus v of phi, you know, so a relativistic scalar with potential. And in particular, if I just focus on, so I can write this out explicitly, but in particular, let's just consider time-dependent profile for this field. I get the usual kinetic minus potential, and that is precisely equal to the pressure, like so.
Okay, thank you.
Yeah, yeah, and it comes from the fact that you know, in this particular case, I'm not keeping any spatial gradients. So the only variation of this guy with respect to the metric would come from varying the spatial, the determinant, and therefore the spatial components will be given by the Lagrangian itself. Yeah. Thanks for that question. Yeah, so this, if you want now, is a consistency check. If I differentiate this pressure with respect to the chemical potential, so I just differentiate this, straightforwardly, I obtain 4m squared over g times mu. And this is just a nice consistency check that what we identified as mu, as the chemical potential, if you want, is indeed correct, because following standard thermodynamics, at the end of the day, the charge density, which is the number density, precisely satisfies the correct relation with respect to mu that it would with the chemical potential, okay? If that makes sense, this is, at the end of the day, a roundabout way to convince ourselves that mu is indeed the chemical potential. And lastly, if you then, so basically this tells us that the number density is linearly proportional to mu. If you plug this back in, you therefore conclude that the equation of state for this particular superfluid, thought of as a function of the number density, scales as a number density squared. Okay, now I want to make, are there any other questions? This basically concludes this simple working example.
Yeah, I have a small question. So to make this the last derivation, we had to set phi field equal to 0. Why is that?
Yes. Why is that?
Yeah,
only because, only because I was interested at this stage in the properties of the condensate itself. So I wanted to know the equation of state of the condensate. You're correct that more generally, if I include now fluctuations of phi, if phi are significantly excited, then I have to take it into account in how it's going to correct the pressure, how it's going to correct the mass density, etc.
I see, thank you.
Yeah. Okay. Okay, so now just to step back a little bit and give the big picture just once more. This was an example from A to Z. It's a simplest example and it's very nice. But just to reiterate the assumptions, we started out from the get-go from a theory of a complex scalar field, okay? And we went down and derived, integrated out the amplitude or the magnitude of this complex scalar, leaving us with an effective theory for the phase, okay? I want to stress that this is a particular example of a superfluid, but there are superfluids whose, you know, quote unquote UV completion is not a complex scalar field, okay? So the phenomenon of superfluidity does not rely on complex scalar fields in the high energy theory, so to speak. Much like in the standard model, the low energy theory, so at scales much below the mass of the Higgs, is simply given by massive SU2 plus SU1. But not every, you know, the completion of this need not be a weakly coupled Higgs field. Okay, it so happens that nature chose that, but it could be much more complicated than this in principle. So similarly with superfluids, there can be other completion of the phonon effective theory, which are not necessarily complex scalars. So that's my point now. I want to say, let us step back and forget about the complex scalar field description and simply ask what is the most general description at low energy of a superfluid. Okay, so the general, if you want, this is the general EFT of superfluidity. So what we know, as we've said from the get-go, superfluidity is the description of spontaneously broken U1, global U1 with finite charge density. Okay, and the relevant excitations, as we know, at low energy and low momentum, all that's relevant at sufficiently low energy and momentum is the Goldstone boson, given that it's massless or gapless. Okay, so the only relevant degree of freedom at sufficiently low energy is what I'm going to call is the Goldstone, and I'm going to call it theta for starters. We'll relate it to pi in a moment. Okay, so this is like the phase of the wave function, if you wish. It's our Goldstone field. The U1 symmetry, which is spontaneously broken, must act nonlinearly on this field. So it acts nonlinearly on theta. And it acts clearly the same as it would on the phase of a wave function, just like it did above, as a shift symmetry on this field. Right, in other words, what we're doing now is simply, as usual with effective field theories, we first of all specify our degrees of freedom, it's theta, and then we specify the symmetries that the theory of theta should satisfy, and then we write down the most general Lagrangian compatible with those symmetries. Okay, so that's exactly what we're doing. So this is the first step. First, we have the non-linearly realized U1 symmetry on pi. And secondly, we also want to, since we're describing non-relativistic physics, we also demand Galilean invariance of the system. In particular, most non-trivial are Galilean boosts. And Galilean boosts, if you remember quantum mechanics, on the phase of the wave function, it acts non-trivially as follows. It shifts theta by m plus v dot x. So v here is the boost velocity, plus the piece which transforms the argument of theta, v dot grad theta proportional to t. So that's what a Galilean boost does on the phase of the wave function from quantum mechanics. So this is a symmetry also that we want to impose. Okay, does that make sense? So we specified everything we need. Now the fact that it is that it should be shift. There's a question. Thank you.
Yeah, thanks. So if U1 is acting non-linearly, then when it gets broken, what does that tell us about the conserved current? Does that change anything about versus a linear U1?
The conserved current is still conserved, but there is yeah. This is an interesting question, right? So, right, when you have linearly realized symmetries, it means that the state you're talking about is invariant under those symmetries. Okay, and therefore it gives rise to statements that correlation functions or scattering amplitudes bracketed with that state will be invariant under that symmetry transformation. When you have a non-linearly realized symmetries, on the other hand, tells you that the ground state is not invariant under that transformation. In fact, what pi does, this Goldstone, is interpolating. It's translating you between different vacua, right? If you think about in the simple example we gave earlier, which was the wine bottle potential, right? What pi does, you start from a vacuum, clearly is not invariant under U1 rotation, but what pi does is it translates you along the trough. And what happens at the level of scattering amplitudes or correlation functions is that instead of having invariance of those correlation functions, you get soft pion theorems, as in QCD, for instance. Okay, so you get correlation function involving a pi field in the limit that pi goes to 0, gets related to a symmetry transformation of correlation functions without pi. Does that answer your question?
That helps, yeah, thank you.
Thanks. Right, so first of all, already from the get-go, since we have shift invariant symmetry, clearly theta cannot appear without derivatives. And so to leading order in derivatives, the Lagrangian must be a function of first derivative of pi. And we know now, I mean, we can make an educated guess because we've just worked out an explicit example. We can guess that the most general effective theory to leading order in derivatives is P of X, okay? Where X, since I'm still working with theta, X is equal to theta dot minus grad theta squared over 2m. And this is the most general effective theory of superfluidity at low energy. You can convince yourself, by the way, as a nice check, that let me denote by star this boost transformation. It's a really nice exercise to show. So convince yourself as an exercise. Show that L being P of X is invariant, or rather it transforms to a total derivative under the Galilean boost star, okay? And this, by the way, this result of L being P of X was proven in a really nice paper by Greider, Wilczek, and Witten. In 1989. From slightly different considerations, but they were able indeed to write this down. And now there's a bunch of things you can derive from this most general P of X. Okay, so I'm going to leave you with some more exercises. These are fun things to check. So first of all, well, it's not really an exercise per se, it's just maybe more of a statement. If you now work at finite charge density, that is to say, now we know what we're talking about. I can take this theta field and expand it around a linearly time-dependent background as mu t plus pi. The corresponding number density, corresponding value of the charge density, n, is simply obtained by differentiating p with respect to mu, or in other words, this is the same as differentiating p with respect to x and setting pi equal to 0. So that's just to say you can derive exactly in generality the relationships we obtained in the previous specific example. And moreover, you can expand this general Lagrangian, right? This P of X, general P of X, you expand it in powers of pi to quadratic order in pi. And you will also recognize a linear dispersion relation for pi with a sound speed. And check this out, this is very nice. You'll find that the sound speed is equal to 1 over m, first derivative of p with respect to mu, divided by second derivatives of p with respect to mu. Okay, that's number one. And by the way, as a check, you can convince yourself if you use the previous p, which was proportional to mu squared, you plug it in, you'll recover the sound speed that we obtained earlier, but this is the more general thing. And now we can do a couple of nice manipulation of this result as follows. So first you notice that I can write this as p comma mu divided by m. And now p comma mu, on the other hand, is precisely partial n partial mu, right? This is precisely, in other words, partial mu partial n. Does that make sense? Because n is equal to partial p partial mu, and therefore the second derivative, if you want, is partial n partial mu. And so this is therefore partial p partial mu, 1 over m, partial mu partial n. And you recognize that this is precisely partial p partial rho, where rho is the mass density. It's equal to the mass of the particle times the number density. So here you recover the well-known hydrodynamical relation for the adiabatic sound speed, that the sound speed squared is dpd rho, okay? So that's a really nice thing to double check. Right, so as before, the choice of P, the physical choice of this Lagrangian, this P, encodes the equation of state, in other words, the type of superfluid that you care to describe, the type of superfluid of relevance. So to give you 3 examples of relevant superfluids. So the first example is the one we considered explicitly before, in some sense the simplest type of superfluid, where P would be proportional to X squared. And this entails that as an equation of state, P as a function of the number density scales as N squared. And as we saw earlier, this is emblematic of scattering processes that are 2 to 2. Okay, this is 2 to 2 scattering. Or equivalently, the low energy potential is given as a quartic potential. So in terms of that complex scalar, just to set our feet on the ground, this corresponded to a quartic potential. Now, for the Mond description that we want to describe, the more relevant case, it turns out, is P of X. If you recall this Bekenstein-Milgram action that we wrote down last time, this would go as X to the 3/2, roughly speaking, okay? So it scales as this non-analytic power. If you recall last lecture, I made a point that this was sort of a non-palatable type of non-analyticity in the kinetic term. But if you work it out as a superfluid effective theory, the corresponding equation of state of this X to the 3/2 is simply N cubed. Okay, which goes to show that as an effective theory of superfluidity, non-analyticity in the kinetic term need not imply non-analyticity in the equation of state. In fact, from a potential, if you work it out from a complex scalar field potential, this is suggestive of 3 to 3 interactions. Where the potential V of psi would be instead given by a hexic potential side of the 6. Okay, so if you work it out starting from a hexic potential, you do exactly the same derivation that we did integrating out the Goldstone, the Higgs, you will obtain an X to the 3/2 theory at the end of the day. The last example is also to highlight the fact that non-analytic powers in P of X is also reasonable to contemplate because there exist in nature known superfluids that have this non-analytic powers. So the famous example, which has been studied in great detail, that it's been a whole hoopla in the statistical mechanics condensed matter community, is the unitary Fermi gas. Okay, so it's a bunch of, well, let me write down the answer first. In this case, P of X scales as X to the 5/2 power. And in terms of N, the corresponding equation of state is identical to that of a free fermion gas. So it's N to the 5/3. And this famous example is the unitary Fermi gas. So it's a gas of fermions there's a question. Yes.
Yeah, kind of just a general question. You lost me a little bit here. Could you explain kind of in general what we're doing with this, how we relate our P of X's and P of N's? And kind of
Yeah. So first, so the procedure is as follows. So given a P of X, okay. Sorry, there's also a question in the chat. Okay. I'll come back to the second question in the chat in a moment. Yes, thank you. Yes. So first of all, P of X. Let's take a different example. Okay, like let's take X to the N, for instance, to be a little bit general. So first of all, the procedure is when you set the photons to zero, the phonons to zero. Okay. As a result, X is simply given by the chemical potential. Sorry, I shouldn't call this N because this will confuse the heck out of me. Let's call this alpha, okay? You set pi to 0, therefore X is just equal to the chemical potential. And as a result, you get the grand canonical equation of state that we described earlier, that P of mu is equal to mu to the alpha, okay? Now you derive the number density from thermodynamic relation as the derivative of P with respect to mu, which therefore gives you that this is proportional to mu to the alpha minus 1. You then invert that relation to get mu as a function of N. And you substitute it back in. to obtain the pressure as a number in terms of the number density. Like that. So this is just to say that specifying this P of X, this Lagrangian, is exactly specifying the equation of state of your superfluid. It is precisely describing what kind of superfluid you're talking about.
Okay,
Does that help?
Thanks for walking through that. Yes, thanks.
Thanks. Okay, and then Joseph has a question online. So he says, could you please explain once more how and why one integrates out the Higgs? Okay, so yeah, that's a great question. So just to scribble, just to go back above a little bit. Right. So we could have started here, and actually I welcome you to do that as a very nice exercise tonight, okay? Here you start out from a theory of a complex scalar field, and you could start out more generally by putting any power here, call it, I don't know, beta, okay, instead of 4. And you just go down this derivation, okay? You still have a conserved current, you can still plug in this ansatz. Here you'll find obviously a different power, okay, for the relationship of the relativistic chemical potential, the same is true. And here's the crucial part. Now you come into the part where you plug in excitations into the Lagrangian, perturbation of the amplitude, perturbation of the phase. And you obtain this kind of Lagrangian, okay? We'll have a kinetic term for rho, some mixing of rho with derivatives of pi, and finally some self-interactions of rho, which of course now will have an exponent that will be different from 4. At this point, you realize that this rho has a mass, it's a massive field. And so to simplify the description at long wavelengths, at low energy, you are justified in integrating out this Higgs field, okay, this radial mode. That, to leading order in derivatives, amounts to treating it as an auxiliary field. So you obtain an algebraic relationship for this field, as we've done here. Now, of course, it's going to be more complicated in the case where it's a general exponent, but you can still solve for it, yada, 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 and you plug it back in to obtain. If you start from a different beta, general beta, you're at the end of the day going to get a different polynomial, monomial, excuse me, for the Lagrangian in terms of X. Okay, I hope this answers Joseph's question.
May I also ask a question?
Yes, by all means.
So it's actually a follow-up now that you said we can set beta there in the Lagrangian where we started, like in the unbroken phase.
Yes.
So my question would be, what then about the vacua and the vacuum stability? Wouldn't we get them depending on what beta we choose?
For sure. Yeah, for sure. Now, I mean, of course, if you start choosing crazy betas, you're gonna, you know, in principle, you may get, I mean, these potentials, they should be somehow well motivated, like, you know, side of the 4th or side of the 6th. But one thing I want to stress, you know, is that I keep trying to give both perspectives, is that superfluidity does not rely on writing down a complex scalar field with some potential. Okay, it's just that simple examples may be cast in this way. But if you go to this particular case of the unitary Fermi gas, which I'll finish that discussion in a moment. But that case of fermionic atoms are strongly coupled, and they're not described by some complex scalar field whose Higgs field you've integrated out. Okay, it's just the UV completion is more complicated. It's just a bunch of fermions.
Okay, thank you.
Yeah, but that's the power of the effective theory. That the effective theory now, that's why I took this path now, this generalized path, is that it doesn't rely anymore on writing down particular complex scalar field theory. That is, in general, the theory of superfluid at low energy. Let me just, of course, if there are other questions, I'm happy to keep going. Let me just perhaps finish the discussion here about the unitary Fermi gas, because it's an interesting example. So what you do, so these are fermions that are interacting with some scattering length. And by tuning an external magnetic field, you can tune this fermion gas to be such that unitarity the unitary limit is saturated for the S-wave cross-section. Okay, so there's some resonance known as a Feshbach resonance where the scattering length diverges. And if you recall from quantum mechanics, when this happens, the S-wave cross-section saturates the unitarity limit. That's why it's called the unitary Fermi gas. Actually, it's a really, I welcome you to read about this on your own. It's a fascinating story. What condensed matter people now understand is that really the notion of a Bose-Einstein condensate on the one hand and a BCS superconductor at the other hand is really one continuous phenomenon. They're not separate phenomenon. It's a whole continuum within which you can dial the scattering length. And when there's a particular transition, when the scattering length diverges, and since the scattering length, in fact, scattering length times the Fermi momentum is the only scale in the problem, the theory becomes scale invariant at that point. And that is what gives rise to this x to the 5/2. Even though it's a strongly coupled system, because it's scale invariant, you can pin down a particular form of P of x. Okay, let's make one more generalization of the story, which pertains to a question that was asked earlier. So far, we've just considered a system of these atoms without any potential ascribed to them, any external potential. So let's now generalize to consider a superfluid in the presence of an external potential. So an external potential, which I'll denote by V of x. And this external potential happily can be space dependent. In general, it will be. So here are the relevant situations we have in mind. For example, for a cold atom gas in the laboratory, this potential would be the trapping potential. Say a harmonic trap for these atoms. Of course, for the case that we're interested in, which is dark matter and galaxies, of course, the external potential is the gravitational potential. So V of x will be equal to m, the mass of the particle, times the gravitational potential phi. The generalization to include such an external potential is absolutely trivial. What happens in this case is that the definition of x gets slightly modified to be x is equal to mu minus V of x plus phi dot minus grad phi squared over 2m. So it just amounts to a redefinition of mu, if you wish. So coming back to a question that was asked earlier, so here mu is still going to be a constant, but because of this V of x, if you want, now the background acquires some spatial profile automatically. So in particular for gravity, which is the case that we are interested in, for gravity, x is equal to mu minus m phi of x plus phi dot minus grad phi squared over 2m. Okay, so at this point, you probably are a little bit, maybe a bit puzzled. How do I know this? How can I justify this? I'll give you two ways to justify that this is the correct way to encode gravity, Newtonian gravity for a superfluid. The first way, so let me put the question why. The first way is to go back to our complex scalar field example. Take that complex scalar field. Sorry, no half. Take that guy and just couple it to gravity, okay? Couple it to gravity, include the gravitational interaction. By the way, that gravitational interaction will be phi times the mass density, sorry, the mass density, which is the mass times psi squared. Okay, so this is the good old m times n, which is which is just rho. Okay, so this is the good old rho times gravitational potential type of interaction. And now just turn the crank. Okay, repeat the entire story. Clearly, when you include this additional contribution, whoops. When you include this additional contribution, this will change this algebraic equation for rho that we had above. We can almost do it in real time in our head, right? What's gonna happen is that this new term, where am I? It's here, right? It will give you a correction in here for the linear piece in rho, and that correction clearly is proportional to m phi. So that's one way to see it, okay? Here's a question.
Yeah, thanks.
Yeah.
So I believe we're adding in Newtonian gravity here, but isn't GR highly relevant for dark matter?
Oh, nice question. I mean, yes, but only in, I mean, not so much, in fact, because you see, for dark matter, how should I say? Right, dark matter is a non-relativistic fluid. So the behavior of dark matter, let's say redshifting, diluting as 1 over the volume, that can be derived non-relativistically. As you know, the Freeman equation for a non-relativistic fluid like dark matter can also be derived on Newtonian grounds. So of course, yes, you're correct, but in particular, ultimately, our primary interest is the behavior inside galaxies. Non-relativistic description is perfectly reasonable. Actually, let me make my answer a little bit more precise because it's a nice question. The Newtonian description that I'm adopting here for simplicity is relevant, right? So this description in terms of the gravitational potential is accurate, provided that we're working on scales r much smaller than the Hubble scale. So r much less than the present day Hubble scale. So for galaxies, clusters of galaxies, it's perfectly appropriate. And now you're correct that if I, really just justifiably want to describe the homogeneous cosmology, then I should couple this to relativistic gravity, but that is also straightforward.
What about for phenomena like lensing? Can you still do the Newtonian description, or do you have to then use GR?
Yeah, great question. Yeah, for lensing, you also need the full metric. That is
right. Of course.
I apologize for that. Yeah, that's a good.
Oh, no worries. Okay, thank you.
Yeah, for lensing, you also need it. All right. So that's one way to see it, and the other way, which is even more direct, is the following exercise. So I'm going to leave this guy to you as an exercise, which is the following. So if you take Newtonian gravity, plus the superfluid, so in other words, the theory is the following. So I add the gravitational term, 1 over 8 pi g, grad phi squared, and I simply add to it p of x, okay? Simply add to it p of x, but x now has this phi in it, gravitational potential. And the exercise is you take this theory and you now vary with respect to phi to obtain evidently a Poisson equation. You vary with respect to phi, and of course you set phi to 0 for simplicity, so no phonons. The exercise is that you'll obtain in the process that the Poisson equation for phi is you'll obtain the following. You'll obtain 4 pi g times the rest mass times the derivative of p with respect to x. And as I said, you set phi equal to 0. Upon doing so, okay, that's what you get. And I hope it's clear, because varying with respect to phi, because phi is hidden within x, will force you to take a derivative of p with respect to x. You set phi to 0, but now you recognize that this quantity p comma x is of course what we've been calling the number density. And so indeed the mass times the number density is precisely the mass density. So you recover the correct Poisson equation by this form. Okay. Okay, I think it's getting a bit late, especially for you guys. I think with the blessing of the organizers, maybe I can take, I don't know, half an hour of the discussion session tomorrow to just finish the story of superfluid dark matter.
Yeah, I think that's the most natural thing. I mean, you can just take it as a spillover.
Spillover, and then it will naturally morph into a discussion.
Yes, exactly.
Perfect. Okay. But let me ask if there are any other questions before you guys.
We need to finish at 7:30 sharp because there's a dinner waiting. This is dinner. So we need to finish in 7 minutes.
Oh, okay.
Yeah. Good.
I have a maybe extremely nice question, but how do we see the superfluidity from all this discussion? This
that's
flow particles.
Yeah, that's actually a really nice question. Thanks for asking it. Yes, so friction, right, is dissipation. You know? So really, indeed, where is it encoded in this discussion that there can be no dissipation? And it's encoded in the fact that our excitations at low energies are given by phonons. They're given by a linear dispersion relation. So, I mean, I can make that more precise next time, but let me perhaps give you the intuitive discussion, which is if you take a body that is moving at a homogeneous velocity, okay, through this superfluid, so let's think of it as an impurity. By Galilean invariance, you can go to the rest frame of this guy. And just like in Lorentz, in the Lorentz case, you know that an electron traveling at constant speed, constant velocity, cannot emit a photon, right? The reason is you go to the rest frame and you can't just spontaneously emit the photon while conserving momentum and energy, yes? So it's exactly the same phenomenon here. You can show that if this body moving at velocity v, where v is subsonic, that's crucial, less than the sound speed, kinematics forbid this body from spontaneously emitting phonons, which is really the only thing that it can do to dissipate energy. Does that make sense? It cannot start dumping energy by exciting phonons, okay? Of course, you can, once the velocity of this impurity exceeds the sound speed, right? If you go supersonic, that's Landau's criterion. The moment you go supersonic, then you can go and start exciting phonons. And that is precisely the superfluid analog of Cherenkov radiation, right? In the medium, if I go faster than the speed of light, I start emitting photons, which then slow me down. Does that answer your question, at least at the intuitive level? That's a really nice question you're asking, by the way.
So the key seems to be to have this linear dispersion relation.
It's exactly that, yeah. Is the fact that these excitations have linear dispersion relation, that dramatically changes the kinematics, which forbids energy dissipation for motions below that sound speed. Yeah.
I see. Thanks a lot.
Yeah, thanks so much. Yeah, great question.
No questions. Okay, so keep going. Justin, do you want to keep going?
No, it's okay. There's 3 minutes, no? So,
yes.
Okay, I think you
next. Okay.
All right, so I guess we'll probably get into this a little bit more the next time. So this phi term that you add in here, this gravitational potential, is this potential of the superfluid with itself, or are we saying this potential is being sourced from something else?
Oh, you mean this capital phi?
Yeah, that's right.
Yeah, in general, it's sourced by everything, including baryons and so forth. Those you would couple as you would normally. Yeah, it's the total gravitational potential, correct.
Okay, all right.
Yeah, because if you want, it's like an external potential. It includes all contributions to the gravitational potential, yeah.
I'm satisfied, thank you.
Okay, I think there are no more questions. So
Great. See you guys tomorrow. Enjoy the dinner.
Let's thank Justin again.
Bye. Bye now.